Go away! How can a small bee make so much sound?
Believe it or not, that noise comes from the bee flapping its wings fast, really fast. Actually, you'll be surprised to know all kinds of sounds are produced and propagated in the same way. This includes the sound that you hear on plucking at a rubber band, the tinny noise our little sister makes by banging a spoon against the vessels, even the sound of music played by your favorite guitarist.
Really? That's interesting. Tell me more.
In this lesson, you will learn about production and propagation of sound and the characteristics of a sound wave. At the end of this lesson, you will be able to define sound, explain how sound is produced, explain how sound propagates from the source to the listener, demonstrate that sound needs a medium to travel, compare longitudinal and transverse waves, identify the main characteristics of a sound wave, and compare the speed of sound in different media. Let's start with what sound is. Sound is a form of energy that produces a sensation of hearing in our ears.
You mean like heat?
Yes, of course. Here's an interesting experiment that proves it. To start, we take a tin can and remove the base and the lid of the can to create a cylinder open on both sides. Then we stretch a balloon around an open end of the cylinder and secure it with a rubber band so that a stretched membrane is formed. We then take a small mirror and stick it to the stretched membrane made out of the balloon on the outer side of the cylinder. Using a laser torch, we focus a light ray on the mirror such that it reflects on a wall as a spot. The final step is to shout in the open end of the cylinder.
This is an experiment.
Did you see how the reflected light spot moved on the wall?
Oh, yes.
If you shout again, it will move again.
This is an experiment.
As we shout, the voice moves because the vibrations are conveyed through the air to the stretched membrane. The stretched membrane gets tuned to the vibrations of the sound. As the membrane vibrates, the mirror on it also flutters. Hence we see the dancing spot. Now let's take a look at two situations where different types of sound are produced. What was common in both the cases where sound was produced? There was a to and fro motion of the parts of the bodies when they produced sound. This to and fro movement of an object is called vibration. Sound is produced due to vibration of objects. In the case of the guitar, it is the vibration of the strings that produced the sound. The buzzing sound is produced by the rapid vibration of the wings of the bee.
Really? It's a little difficult to believe.
Well, let's verify whether it is true through an experiment that should help convince you. Let's take a bell and ring it. Do you hear that sound? This ringing sound is due to the vibration of the bell's gong. Now, suspend a table tennis ball with a string to a stand. And then gently bring the ball in contact with the ringing bell. You will be able to see the ball flicker away from the bell and start swinging. This is because the bell is vibrating. This confirms that the sound of the bell was being produced due to vibrations. What is the difference between the sound emitted by a lion's roar and the sound produced by the rustling of leaves? A lion's roar is a high-intensity sound, while rustling of leaves is a low-intensity sound. Intensity of sound is the amount of sound energy incident per unit time per unit area. The sound intensity is normally measured in watt per square meter. To reach your ear, sound needs to propagate from the source to you through a medium. A medium is the matter through which the sound is transmitted. A medium can be liquid, solid, or gas.
So how does sound travel? Do the particles in the medium travel from the source to the listener?
No, not really. To understand the process of the propagation of sound, let's analyze what happens when we cause a vibration to produce sound. Now, let's see. What happens when we stretch a rubber band and plug it in the middle? The air particles of the medium, which are in contact with the vibrating rubber band, that is, the source of sound, are first displaced from their state of rest. These displaced air particles displace their neighboring particles and then come back to rest in their original positions. Thus, now another set of particles of air between the vibrating rubber band and the listener are in a state of vibration. These particles vibrate in a direction parallel to the line joining the rubber band and the listener. They in turn displace neighboring particles before returning to a state of rest. This process continues until the sound reaches the listener. As you can see, particles of the medium do not move from the source to the listener, but it is the disturbance in the particles that is carried forward to the listener. This kind of a disturbance is called a wave. In other words, a wave is a disturbance that moves through a medium when the particles of the medium set neighboring particles into vibration. Therefore, we visualize sound in the form of waves. Air is the most common medium through which sound propagates. To study the sound waveform in more detail, let's use a tuning fork. Vibrating a tuning fork produces a small audible sound. Vibration involves to and fro motion of the prongs of the fork about a fixed point. This fixed point is also referred to as the mean position. The vibrating prongs of the tuning fork push and compress the particles in front when moving towards the outer direction, creating a region of high pressure. In this region of high pressure, the density of air is higher than the normal. This region of high pressure is called compression. When the prong moves backwards, it creates a region of low pressure, called rarefaction. In this region, the density of air is lower than the normal. Thus, as the tuning fork vibrates, the to and fro motion of the prongs of the fork create a series of compressions and rarefactions in the air between the fork and the listener. These compressions and rarefactions comprise a sound wave that propagates through the medium. As sound waves, travel as disturbances propagated through air by a mechanism of particle-to-particle interaction. They are termed as mechanical waves. Mechanical waves require a material medium for their propagation. A mechanical wave can be a transverse wave or a longitudinal wave. Sound waves in air are longitudinal waves. To understand what that implies, we need to first understand the two categories of waves. In transverse waves, the particles of the medium vibrate up and down about their mean position, which is in the direction perpendicular to the direction of wave propagation. When we fix one end of a string and vibrate the other end in a direction perpendicular to the length of the string, the wave pattern that is seen is that of a transverse wave. When a pebble is thrown onto the surface of still water, it creates small ripples. These ripples propagate through the expanse of the water as transverse waves. In fact, try and observe closely tiny particles and dried leaves on the surface when ripples are formed. These particles do not go with the wave, but just move up and down at their positions about a mean position. This figure depicts the propagation of a transverse wave. You will learn more about transverse waves in higher classes. In longitudinal waves, the direction of vibration of the particles in the medium is parallel to the direction of propagation of the wave. The wave pattern set in a slinky is an example of a longitudinal wave. Let's recall the tuning fork experiment. In sound waves produced by a tuning fork, particles of the medium vibrate in a direction parallel to the direction of wave propagation. This produces compressions and rarefactions in the wave, similar to that in the pattern showed by a slinky. Thus, we can see that sound waves in air are longitudinal waves. A complete sound wave can be considered as the repetition of the pattern of a single wave. That is, it comprises a number of compressions and rarefactions in succession. The length of a single wave is called wavelength. In other words, wavelength is the distance between two consecutive compressions or two consecutive rarefactions. It is denoted by the Greek letter lambda. Since a compression and a rarefaction follow each other in succession, sound propagation is a periodic phenomenon. The interval between the generation of two successive compressions or two successive rarefactions is constant and is referred to as the time period of the wave. Time period is denoted by t and is measured in seconds. For example, the time taken by a pendulum to complete one to and fro cycle is known as its time period. All of us have heard a clock tick. It ticks once every second and maintains the time period. The ticking of a clock once every second is the frequency of the clock. Frequency of sound is the number of waves produced in unit time. It is denoted by the letter N and is measured in hertz. Since the clock ticks once per second, its frequency is 1 hertz. Let's see how frequency relates to time period. The relationship between frequency and time period can be expressed as n is equal to 1 divided by t, where t is the time period, Thus, if the time period of a wave is 1/10 of a second, then we get 10 waves in 1 second. The frequency of this wave is 10 Hz.
Ouch!
Yes, that hurt, didn't it? But listen to the cooing of this pigeon. Not so bad, was it? Why do you think the effect of both the sounds on our ears is so different?
Well, because our ears are not used to loud noises.
That's true too. The technical explanation, though, is related to a concept called pitch of sound. The pitch is the interpretation of frequency of a sound by the brain. Commonly, pitch is taken as the frequency of sound. A scream is a high-pitched sound, since the frequency of a scream is high. Similarly, the cooing of a pigeon is a low-pitched sound. The shorter the wavelength, the higher the frequency, and the higher the pitch of the sound. Simply put, short waves sound high. Long waves sound low. Let's listen to some music. Can you tell whether it is a single instrument or two instruments playing?
Yes, it is definitely two instruments. One sounds like a violin and the other could be a sitar.
You could identify the difference in instruments because of the type of sound you heard, right?
Yes.
Sound emitted by every instrument has a unique characteristic that distinguishes it from other sounds with the same pitch or loudness. This characteristic is the quality or the timbre of the sound. If you now listen to each of the instruments playing the same tune separately, here you can make out the difference in quality of both the sounds. Sometimes when you switch on your computer, you hear a long beep indicating a boot-up error. Listening carefully, you make out that this beep is a uniform sound. This beep sound has a single frequency. Thus, the sound wave shows uniformity. This is an example of a tone. A tone is a sound wave of single frequency. The man on the left seems to be listening to some good music. Proper mixture of frequencies results in a pleasant sound or note, which we term as music or musical note. Thus, a note is a sound produced due to a blend of several frequencies. If a note is not pleasant to hear, it's simply called noise. Now, listen to these sounds. Can you hear me? Can you hear me? What was the difference?
One sound was loud and the other was very soft. What makes these sounds different?
It is a characteristic called amplitude. The loudness of a sound depends on its amplitude. Amplitude of a sound wave is the maximum displacement of the vibrating particles from their mean position. It is represented by the letter A and depends on the force with which an object is vibrated. Greater the amplitude, louder the sound head, and lesser the amplitude, the lower the audibility of the sound. Listen to these two sounds produced by the same drum. The second sound was louder than the first. This is because the amplitude of the sound produced the second time was higher. A loud sound can travel across a larger distance because it is associated with high energy.
What about the speed of sound though? How fast can it travel?
Comparatively speaking, the speed of sound is less than that of light. If you notice, on stormy days, we see the lightning first and then hear the thunder. That's because light travels faster than sound, and so lightning reaches us first. Speed is the ratio of unit distance to unit time. For a sound wave, the unit distance is its wavelength, lambda. And the unit time is the time period t. Therefore, the speed of a sound wave is the ratio of its wavelength to its time period. It is denoted by the alphabet V. You know that the reciprocal of a time period of a sound wave is equal to its frequency. Therefore, the speed of a sound wave is the product of its frequency n and wavelength lambda.
What about the speed of sound in a medium other than air?
Well, that differs from medium to medium. The speed of sound depends on the properties of the medium through which it propagates. The important properties that affect the speed of sound are the temperature and the density of the medium. If the temperature of a gas increases, its density decreases, resulting in an increase in the speed of sound and vice versa. The speed of sound in various media at specific temperatures is given in the table. From this table, you can see that sound waves propagate faster in solids than in liquids and gases.
And what happens when an object is moving faster than sound can move in that medium?
Very good question. Have you ever heard of sonic booms? When an object is traveling at a speed greater than the speed of sound in air, it is said to be at a supersonic speed. For example, a bullet fired from a gun travels at a supersonic speed. Some jet aircrafts, at times, travel at supersonic speeds. When an object, like a jet aircraft, travels at supersonic speed, it produces shock waves in the surrounding air. These waves carry enormous energy. This energy is propagated in the form of a sharp and loud sound called the sonic boom.
But then, what happens when there is no air or no other medium? What happens to a sound produced in such a situation?
Sound cannot travel in the absence of a medium. We know that the sun is a huge ball of fire. The reactions of gases in the sun result in explosions that produce light as well as sound. Why do you think we are able to see the sun's light, but not hear the sounds of these explosions? Because sound needs a medium to travel. We just said that sound needs a medium to travel. Let's verify this through an experiment. We take an electric bell and fit it in an airtight glass bell jar. The bell jar is connected to a vacuum pump from one end and a power supply with an on or off switch at the other end. On pressing the switch, you will be able to hear the bell ringing. Now suck out all the air from the bell jar using a vacuum pump. You will notice that as the air is being sucked out, the sound of the bell starts getting feebler. In fact, the sound of the bell is not audible at all once all the air in the bell jar is sucked out. That's because absence of air has created a vacuum inside the jar, meaning there is no medium in the jar now. This confirms that sound needs a medium to propagate. This brings us to the end of this lesson on production and propagation of sound. In this lesson, you learned how sound is produced and propagated. You also learned about longitudinal waves and transverse waves in relation to sound waves. Finally, you learned about some important characteristics of sound waves. The section on solved problems provides you an opportunity to review some model problems based on these concepts. Can you calibrate a stopwatch to directly show the depth at which the water is present? You can find clues to solve such a problem in Solved Problem 3. To revisit the key points covered in this lesson, please review the flashcard at the end of this lesson.
Hello!
As you can see, if you speak loudly in mountainous areas, it seems like the mountains are responding right back. We commonly call this response an echo. Let's consider another example. Golconda, a ruined fort in south-central India, is situated west of Hyderabad. One of the famous engineering marvels at Golconda is the fantastic acoustic effects used to maintain security in the fort. A hand clap at a certain point below the dome at the entrance of the fort can be heard clearly at the highest point in the fort, located almost a kilometer away. This hand clap worked as a warning note to the ruins residing in the fort in case of an attack. Why do we hear echoes? Well, like light, sound also reflects off objects. Reflection of sounds lead to such phenomena as echoes. In this lesson, you will learn about the reflection of sound. At the end of this lesson, you will be able to define reflection of sound, verify laws of reflection of sound, explain the concept of an echo, calculate the minimum distance required to hear an echo, list the applications of multiple reflection, define reverberation, explain the structure of the human ear, define the ranges of hearing for infrasonic sound, audible sound, and ultrasonic sound. list the applications of ultrasound and define sonar. Look at this ball. When it is thrown on a hard surface, it bounces back. Light as well as sound waves behave in a similar manner. When light rays are incident on a reflecting surface, they bounce back. Similarly, a sound wave incident on a hard surface bounces back into the same medium. This is known as the reflection of sound. According to the laws of reflection of sound, the direction in which the sound wave is incident and the direction in which it is reflected make equal angles with the normal to the reflecting surface at the point of incidence. The incident sound wave, the reflected wave, and the normal at the point of incidence are in the same plane. Sound waves need polished or rough surfaced obstacles to get reflected. Let's verify these laws through an experiment. To set up the experiment, we take two identical hollow pipes, PQ and RS, each about 2 feet long. We place these pipes on the surface of a table near a wall so that their axes intersect at point O on the wall as shown. Then, we keep a clock near the end P of the pipe. Finally, keep a cardboard vertically in between the pipes, so that the sound of the clock at P cannot be heard directly at the end S of the pipe RS. Now we try to hear the sound of the clock from the end S of the pipe RS. The angle of the pipe RS can be changed by tilting it in a horizontal plane about the point O. The sound is very feeble, isn't it? That's a little better. Wow, that's quite clear, right? Oh ho, this angle is not so good. The sound has become feeble again. A feeble ticking sound can be heard through the pipe RS in random positions. Fix the position of the pipe RS at the angle where the loudness of the sound heard is maximum. Let's now measure the angle between the axis of the pipe PQ and the normal to the wall at the point O. This is the angle of incidence, I, for the incident sound wave. Now, we'll measure the angle between the axis of the pipe, RS, and the normal to the wall at the point O. This is the angle of reflection, R, for the reflected sound wave. You can see that the angle of incidence is equal to the angle of reflection. Now, try changing the orientation of the pipe, RS, by tilting it vertically. The audibility, that is, the loudness of the reflected sound, decreases. This is because, when tilted vertically, the plane of the reflected sound wave is different from the plane of the incident sound wave. In this situation, only parts of the reflected sound wave pass through the pipe RS. This confirms that the incident wave, the reflected wave, and the normal all lie in the same plane. We already saw what happens when you shout in an open air in the mountains. Let's now observe this boy shouting into a well.
This is an experiment.
Did you hear that? That was the boy's voice reflected back from the water in the well. In our daily lives, we call this sort of a reflection an echo. Thus, an echo is repetition of sound that results as a reflection from a surface. Here's an interesting fact about the origin of the word echo. According to Greek mythology, Echo was a nymph who had the job of talking incessantly to Hera, the queen of gods, so that her husband Zeus would not get caught in his misdeeds. Hera caught on to Echo's tricks and cursed her to only be able to say what others had just said. Thus, reflection of sound can be attributed to Echo talking under the curse, repeating what you say.
Hello!
You may be wondering why you don't hear an echo for reflection of every sound. To explain this, let's observe a scenario where a man standing in front of a cliff shouts, "Hello."
Hello! Hello!
Did you hear that? There was a clear echo. Now, let's see what happens if the man moves closer to the cliff and shouts, "Hello" again.
Hello!
In this case, there was no echo when the man shouted. Why do you think you could hear an echo in the first position but not in the second? Try and analyze what changed in the second situation. Nothing but the distance of the man from the cliff, right? It is the distance that is making a difference. We cannot hear an echo unless the reflecting surface is beyond a specified distance from the source of the sound. In this case, it was the man shouting hello. To find out how this works, let's examine how our brain processes sound. The sensation of sound persists in our brain for 0.1 second. Therefore, to identify an echo, the time interval between the reception of the original sound and the reflected sounds should be at least 0.1 second. So, how much distance do we need between the source of a sound and the reflecting surface to be sure that we will be able to hear an echo? Let's find out. The speed of sound at a given temperature, say 22 degrees Celsius, is 344 meters per second. Consider the echo produced by shouting on a cliff. Let d be the distance between the source of sound, in this case, the man, and the obstacle, in this case, the cliff. The distance travelled by the sound wave from the source to the obstacle and back to the source is equal to 2d. To hear the echo, the duration in which the reflected sound travels back should be at least 0.1 second. Therefore, by using the expression of speed, the distance travelled by the sound wave is equal to the product of the speed of the sound and the time for which a sound persists in our brain. On substituting the values and simplifying, we get the distance is equal to 17.2 meters. Therefore, the minimum distance required to hear an echo is 17.2 meters. Note, this distance will change with the temperature of air, as the speed of sound changes with the temperature of air. When you hear thunder rolling, the sound continues for some time. The rolling of thunder is due to the successive reflections of sound from a number of reflecting surfaces, such as the clouds and land. This is called multiple reflection of sound. Thus, multiple reflection of sound is the successive reflection of sound from various reflecting surfaces. We find many useful applications of multiple reflections of sound in our daily life. A doctor using a stethoscope to give you a checkup is a very common sight. A stethoscope uses the principle of multi-reflections to help the doctor hear your heartbeat. Let's take a look at how it works. The chest piece of the stethoscope consists of a plastic disc called the diaphragm, which is placed on the patient's body. the sound of the heartbeat vibrates the disc. These vibrations produce pressure waves which travel to the listener's ears through the hollow tubes by a series of multiple reflections throughout the tubes. There are various other applications of multiple reflections. Megaphones, horns, and musical instruments like trumpets are designed to magnify amplitude of the sound and reflect and propagate sound waves in a particular direction. The curved ceilings of cinema halls and conference halls are also designed keeping the principles of multiple reflections in mind. The curve in the ceiling ensures that the sound is reflected to all the corners of the hall, so that there is an even distribution of sound. In some cases, a soundboard is positioned behind the stage so that the sound waves produced are spread across the hall evenly. However, in cases where these halls are not designed properly, multiple reflections can lead to uneven distribution of sound. Let's see what causes this problem. Consider a big closed room where a source S, a speaker, and an observer O are in the positions as shown. The observer may hear more than one reflection of sound produced by the source. This is due to the multiple reflections produced at different locations on the walls and in the room. This can make it difficult for the observer to focus on what the speaker is saying and hear him clearly. The reflected sound is heard until its intensity is reduced to a value where it is no longer audible. Finally, the sound fades off completely. Thus, the observer hears the sound produced by the source persistently till it fades away beyond audibility. This phenomenon of persistence of sound in a closed enclosure, due to the multiple reflections of sound in an enclosure, is called reverberation. Reverberation is generally minimized in auditoriums by covering the walls, the ceiling, and the flooring using sound-absorbent material like cardboard, thick curtains, and fiber. Sound as a concept would not exist for us if we could not hear it, right? Therefore, an explanation of the reflection of sound is incomplete without a look at the mechanism that enables us to hear, the human ear. The ear converts audible sound waves in air into electric impulses that reach the brain, enabling us to hear. Here, you can see the structure of the human ear. The human ear is categorized into three main parts: the outer ear, middle ear, and the inner ear. Let's see how these parts work together to produce the sensation of hearing. The outer ear, called the pinna, allows sound waves to pass into the ear through the auditory canal. At the end of this canal is the eardrum or the tympanic membrane. When a compression or rarefaction reaches the eardrum, it pushes or pulls the eardrum inward or outward respectively due to the pressure on the outer side of the membrane. The middle ear is comprised of three bones: the hammer, anvil, and the stirrup. These bones amplify the vibration and transmit the pressure variations of the sound waves to the inner ear. The inner ear is comprised of various parts, including the cochlea and an auditory nerve. The cochlea converts the pressure variations into electrical signals. Then, these signals are transmitted to the brain through the auditory nerve. These electrical signals are interpreted by the brain as the appropriate kind of sound. Hearing aids help us compensate for any shortcomings in our hearing capabilities. So, how does a hearing aid work? A hearing aid is a battery-operated device that receives sound waves through a microphone. This microphone converts sound waves into electrical signals, which are amplified by an amplifier. The amplified signals are sent to the speaker of the hearing aid. The speaker converts them into sound waves and sends them into the ear at a volume that the ear can clearly hear. The buzzing of a bee is clearly audible. In fact, sometimes we wish it wasn't so loud. However, though we can see the pendulum vibrating, it doesn't seem to be producing a sound. Look at the boys straining to hear the sound of the pendulum. We are unable to hear some of the sounds produced around us because sounds vary in their frequencies. A human ear can only hear sounds that are within a frequency of 20 Hz to 20,000 Hz. This range of frequency is called the audible range. We cannot hear sounds with a frequency lesser or greater than this audible range. However, the audible range for different species is different. Dogs, for example, have an audible range much higher than that of humans. That's why people have watchdogs. Dogs can hear many sounds that are not audible to human ear. The table shows the hearing range for 3 animals. Dogs can hear sound waves ranging from 18 kHz to 22 kHz. Rhinoceros can hear sound waves ranging from 0 Hz to 5 Hz. Bats can hear sound waves ranging from 0 Hz to 100 kHz. Sound waves that have a frequency less than 20 Hz are called infrasonic sound waves. These are also referred to as infrasound waves or infrasonics. Similarly, sound waves that have a frequency greater than 20,000 Hz are called ultrasonic sound waves. These are also referred to as ultrasounds or ultrasonics. A summary of the various ranges of sounds is shown here. What does the word ultrasound remind you of? Yes, it commonly refers an ultrasound scan that helps check on the health of a baby in a womb. Ultrasound scanners enable us to obtain images of internal organs of the human body. Even though we cannot hear them with our naked ears, ultrasonic sound waves have a wide range of applications in several fields, such as medicine and industry. For example, ultrasounds are used in a technique called echocardiography. This technique is used to diagnose any defects in the heart by obtaining the image of the heart. Ultrasonic waves are made to reflect from various parts of the heart, and the reflected waves form the image of the heart. Ultrasounds are also used for medical treatment. For example, it is used to help people suffering from kidney stones. Ultrasound waves are used to break the stones into fine grains so that they can be released from the body through the excretory system. In industrial applications, ultrasounds are generally used to clean parts located in hard-to-reach places. For example, in spiral tubes, odd-shaped parts, and electronic components. Here's how the cleaning is done. The relevant object is put in a cleaning solution, and these sound waves are sent into that solution. Due to the high frequency of the waves, the dust and dirt particles detach from the object, leaving it clean and dust-free. Ultrasounds can also be used to detect cracks and defects in metal blocks. Cracks or air bubbles present inside a metal block are invisible from the outside. To detect these cracks, ultrasonic waves are passed through the metal block. And detectors are placed on the other side of the block to detect the transmitted waves. On encountering a crack or an air bubble, the ultrasound gets reflected back, indicating the presence of the defect. Sonar stands for Sound, Navigation and Ranging. Sonar is a device that uses ultrasonic waves to measure the distance, direction, and speed of underwater objects, or the depth of sea beds. It consists of a transmitter and a detector fitted at the bottom of a ship. Let's see how it works. The transmitter produces and transmits ultrasonic waves that travel through water and reflect back after striking objects or the seabed. The detector catches the reflected rays and converts the ultrasonic waves into electrical signals, which can be suitably interpreted. The distance of the object that reflected the sound wave is calculated using the speed of sound in water and the time interval between emission and reception of the ultrasound. This technique is useful in determining the depth of the sea and to locate underwater hills, valleys, submarines, icebergs, and sunken ships. Let's consider an example where we use this technique to determine the depth of the sea. Let the distance from the ship to the seabed be d. The sound wave sent to the seabed has to travel twice the distance from the ship to the seabed. That is, from the transmitter to the seabed and back to the receiver. Twice the distance d is equal to the product of the speed of the sound wave in water, v, and the time interval between emission and reception of the ultrasound. Thus, the depth of the seabed is equal to half the product of speed of the sound and the time interval. Here is an example of a species that uses its personal sonar to obtain its food. A bat emits high-pitched ultrasonic squeaks that hit the obstacle or the prey and reflect back to the bat's ears. Based on the reflections received, the bat is able to determine the nature and location of its prey. This brings you to the end of this lesson on reflection of sound. In this lesson, you learned how reflection of sound results in echoes and reverberation. You also learned about applications of reflection of sound and the working of the human ear.